Dear students, today we will discuss the continuation of electric flux. First, electric flux will recollect once. A group of electric field lines passing through a given area, that is E bar dot A bar, where E bar is electric field and A bar is a area vector. Since electric field is a vector quantity, area vector is a vector quantity, and area vector is nothing but it is perpendicularly outward direction. So the electric flux is equal to E bar dot A bar into EA cos theta. If A is a constant, and straight away we can use, if A is not a constant, then we have to take a small elementary area and then we need to integrate over here, E bar dot A bar whole surface integral, we need to go for electric flux. Now this continuation, electric flux through a disk, we will discuss. So electric flux through a disk. Let us suppose there is a point charge plus q, positive charge, plus q is placed, and then at a distance L there is a disk of radius r present over here. So the disk is placed like this, and then from this the electric field lines originate positive charge and then continuously the passes through the disk. Then the extreme ends, if you observe, it looks like this. Then the angle subtended over here, whatever it is present over here, this angle represents a solid angle. So the solid angle, by using the solid angle to find the electric flux through the disk, I will discuss in the coming section. And the right now over here, that electric field lines passes through a disk. Since the electric field lines passes through a disk over here, the amount of electric flux passing through a disk, if you want to measure over here, the extreme ends of electric field lines looks like a solid cone, or it looks like a conical shape. Since it looks like a conical shape over here, then first we have to take an elementary strip over here at a distance r with a radius x. The thickness of the elementary strip is dx, and the radius of this disk is r. The elementary strip having a radius is x. Then the elementary strip, if you assume over here that the area vector and the electric field lines from a positive charge, it passes along this direction. Then the angle between here area vector and then the electric field vector will be angle theta, we can say. Then the electric flux is equal to E bar dot A bar, that is EA cos theta, we can say. Then the electric field intensity at the rim over here, if you observe that each and every position that electric field remains constant, because the ring is present like this, and then at every position if you observe that electric field remains constant from this point charge. Then the electric field intensity E is equal to 1 by 4 pi epsilon naught to the charge present is q. The distance from here to here is root of L square plus x square whole square. So that is L square plus x square, we can say. This is electric field intensity passing through the elementary ring over here. Then the area present over here is circumference 2 pi x, and the thickness of this disk is dx. Then angle present over here is theta. Since over here if I assume theta, obviously horizontal it makes an angle theta, we can say. Then electric flux is equal to, in place of E, dA and then cos theta. Then the electric flux is equal to, in place of E, 1 by 4 pi epsilon naught q upon x square plus L square. We can substitute over here 1 by 4 pi epsilon naught q by L square plus x square. This is electric field intensity, and the area vector over here, area is 2 pi x dx. And then of course area vector is perpendicularly along this direction, 2 pi x dx, and then cos theta, if you observe over here, adjacent side by hypotenuse, that is L upon root of L square plus x square, we can say. So whenever we want to find the electric flux through a disk, we have to take for a continuous distribution surface, if we consider, we need to consider the elementary strip. Over the elementary strip, the amount of electric field passing through the area of the strip and then the cos theta value will be, we have to write. Then if you simplify over here, the electric flux is equal to, suppose here small elementary strip we are finding, small amount of flux is passing through the strip. So d phi is equal qx dx into L upon 2 into L square plus x square whole power 3 by 2. Qx dx L is numerator and 2 epsilon naught L square plus x square whole power 3 by 2. So this will be the flux passing through the ring, the elementary ring which we consider. We have to go for integrate. This total flux will get as a phi, and we have to integrate from the elements we can consider over here from center to the center x is equal 0 and the top end at x is equal r we can say over here. So from integration 0 to r we have to go for integration. So when we integrate, then we will get as that flux phi is equal over here q L by 2 epsilon naught. I can bring out, remaining terms will be 0 to r x dx upon x square plus L square whole power 3 by 2 we can say. This is the flux we can say. Then let, for integrating purpose in easiest format, let x square plus L square is equal, let us suppose z square if I say for example. Then for the ring, as I told you, the length remains constant for the elementary rings from 0 to r. Then if I differentiate over here, this L square is a constant and differentiate with some quantity, 2x dx is equal 2z dz. Then in place of x dx I can write z dz. Then the flux is equal ql by 2 epsilon naught 0 to r z dz upon here x square plus L square z square whole power 3 by 2. We can say over here that z cube. Here z and then square gets cancelled. Then we can write in the next step integration of 1 by z square dz is that minus 1 by z. So the flux phi is equal ql by 2 epsilon naught into integration of 1 by z square is minus 1 by z. This minus I brought out over here 1 by z from 0 to r we can say. Then since z is nothing but root of x square plus L square. So the electric flux is equal to ql by 2 epsilon naught, of course minus is there, 1 by, in place of z I can write over here that x square plus L square. Here the variable is x. So in place of x, upper limit minus lower limit, if I write minus ql by 2 epsilon naught into 1 by root of r square plus L square minus 1 by L we can say 0 plus L square L minus, if I multiply over here, that ql by 2 epsilon naught into 1 by L minus 1 by root of r square plus L square. So L also if I multiply inside, the electric flux through the ring, through the disc will be q by 2 epsilon naught 1 minus L upon root of r square plus L square. This is the expression for the flux through the disc over here. Then the next analysis over here, if we consider electric flux through the lateral surface for a cylinder due to a point charge, we will discuss. So same electric flux through the disc by knowing the analyzing the solid angle. By using the solid angle, again I will discuss, we will get same expression, but in easiest format that is there. Since it is the method which I am giving you, the electric flux concept, by using electric flux concept only. Now electric flux through a lateral surface of a cylinder, lateral surface of a cylinder. The pehle ka case, in the previous case we discussed that electric flux through a disc, and now electric flux through a cylinder, that is due to through lateral surface of a cylinder due to a point charge. Lateral surface of a cylinder, due to point charge. This point charge is placed at the center of the cylinder. So consider a cylinder of radius r, consider a cylinder of radius r, the length of the cylinder is L, and let us suppose a point charge q is placed at the center. A point charge q is placed at the center, and the radius of this cylinder is r. Then, as I told you, to find the electric flux through a continuous distribution surface, we need to take a elementary strips. Here elementary strips I am taking at a distance x over here. At a distance x, the center is at a distance x, of course the radius will be remains r, of course. Then due to this point charge, the direction of electric field will be of course away. So the electric field intensity at this point will be along this direction. This is the direction of electric field intensity. And since over here lateral surface, if I say, this will be the area vector, then the angle present over here is theta, if I say. Then obviously over here the horizon with the ring, the elementary strip whatever we consider, here also vertically makes an angle theta over here. Since over here has theta over here, first what is the value of electric field intensity? Here the distance from point charge to the elementary strip x at a center is having a distance as x, if I say, this distance we have to write over here that r square plus x square we can say. Then the electric field intensity over here E is equal to 1 by 4 pi epsilon naught, charge present is q, r square plus x square. R square plus x square. Here variable is x. Since r square plus x square, root whole square, square and root and gets cancelled. And here area, if we consider over here, the area of this elementary strip over here, that 2 pi r, the circumference of the ring is that, our circumference of the ring is 2 pi r, and the thickness of this elementary part is dx, because at a distance x I consider, the elementary strip is having a very small thickness dx. So circumference into thickness gives the area of this strip, and the angle between area vector and the electric field will be theta. So the electric flux is equal E ds cos theta or E dA cos theta we can say. Then the electric flux phi is equal, in place of E I can write over here 1 by 4 pi epsilon naught q upon r square plus x square. Actually here root of r square plus x square and then square is there, square and then root gets cancelled. And then E and then dA. dA is the area of the strip, that is we have written over here 2 pi r into dx. E dA cos theta over here. The cos theta, if you see adjacent side by hypotenuse, that is r upon root of r square plus x square. E dA cos theta. Whenever we are finding the electric flux through a distribution or continuous surface distribution, we have to consider that electric field intensity and then the area of the strip. So E dA cos theta. So here E dA cos theta I substitute over here. So this is the elementary strips flux. So that small amount of flux I can say over here that d phi. Now we have to go for integrate. So before integrate, just I will rearrange the terms over here. 2 pi gets cancelled with 2, and here r is there, r square. Q r square dx upon 2 epsilon naught into r square plus x square whole power 3 by 2, power 1 and power 1 by 2. So q r square dx by 2 epsilon naught r square plus x square whole power 3 by 2. Then I have to go for integrate. So we need to integrate with the limits over here. Since the point charge is at the center, the left end is having a distance over here L by 2. If point charge is at the origin, we can say over here that minus L by 2 has a lower limit, because the first elementary strip we can consider over here. Then with respect to point charge left side over here, the distance is minus L by 2 and this will be plus L by 2. So we have to go for integrate from minus L by 2 to plus L by 2. So here integration of d phi, the total flux will get as phi q r square upon 2 epsilon naught, because here x is variable. So here integration is a function of x. So minus L by 2 to plus L by 2, the remaining term will be dx upon r square plus x square whole power 3 by 2. Then we have to go for integrate. So to integrate over here, simplest format, if I observe that from this diagram tan theta is equal to opposite by adjacent. So, the tan theta is equal to, here opposite is x and adjacent is r. So, the tan theta is equal to x upon r. So, I can write over here in place of x is equal to r tan theta. Then if I differentiate with some quantity, I will get as dx is equal r secant square theta and then d theta. Then we can substitute the dx value in place of x r tan theta. If I substitute, I will get over here that, over here, before that I will eliminate over here r square plus x square plus in place of x r tan theta. So, r square tan square theta. Then I will get over here that r square, if I take common 1 plus tan square theta, this should be r square secant square theta, we can say. Then by substituting over here, I will get that the electric flux is equal to, electric flux is equal, by substituting over here, q r square upon 2 epsilon naught from minus L by 2 to plus L by 2. In place of dx, we have to substitute this r secant square theta and then d theta by r square plus x square value, we got r square secant square theta, r square secant square theta whole power 3 by 2. Here if you observe over here, the 2 gets cancelled. Since 2 gets cancelled with square, then the remaining term over here, flux is equal q r square upon 2 epsilon naught minus L by 2 to plus L by 2 r secant square theta d theta upon r cube secant cube theta. Here r secant theta whole power 3 is present. Then here r square r and then r cube gets cancelled and secant square theta and then cube gets cancelled. Then the remaining term will be phi is equal to q by 2 epsilon naught from minus L by 2 to plus L by 2 1 upon secant theta. I can say over here that cos theta and then d theta. Then after integrating over here, integration of cos theta, we can say over here that integration of cos theta is sin theta. Integration of sin theta is minus cos theta. We have to take care about the value of integration. So, flux is equal to q upon 2 epsilon naught, integration of cos theta is sin theta from minus L by 2 to plus L by 2. Here integration is a function of distance, and in place of sin theta, by the diagram, from the diagram if you observe q upon 2 epsilon naught, in place of, by go through the diagram, sin theta is equal to opposite by hypotenuse. So, we will get x upon root of L square plus x square, we can say, minus L by 2 to plus L by 2. Then phi is equal, flux is equal to q by 2 epsilon naught. In place of x, first upper limit will substitute, that is I will get over here L by 2 under root of L square plus L square by 4. I think so here not L square plus x square, it is a r square plus x square, because the radius of the strip is capital R. So that radius of the cylinder is capital R over here, we can say over here that straight away r square plus x square. So, in place of x we have to substitute, and then minus, again lower limit if you observe, minus L by 2 upon root of r square plus L square by 4, minus into minus plus. Then the flux is equal to q by 2 epsilon naught, here minus into minus plus L by 2, L by 2 plus L by 2 will be L, we can say straight away, L upon root of, the denominator if I take as LCM as 4, L square plus 4r square, we can say. And then this root 4 goes numerator. So, I can write over here that flux is equal to q by epsilon naught into 2L by root of L square plus 4r square, we can say. Here finally 2 gets cancelled, the flux through the lateral surface, you will get that flux through the lateral surface, we can express over here that q upon epsilon naught into L by root of L square plus 4r square, we can say. This is the flux through the lateral surface, we can say. So, the electric flux how to find, I hope so you understood. And the third kind of analysis we will discuss over here, that electric flux due to a point charge, electric flux due to a point charge we will discuss. So, previous two cases through the disk and that through the cylinder, that to the cylinder through the lateral surface. Now, flux produced by a point charge. Flux produced, electric flux produced by point charge. So, to understand our here electric flux produced by point charge, let us suppose you consider that a point charge is placed over here Q. To understand the purpose over here, that I am considering that a semi circular or semi sphere we can say, or I am closing over here of course. To understand purpose I am considering over here. Since the charge is placed at the center over here, then from this the electric field lines will be moves in all the directions. So, the radius of this sphere I am writing as R. Since over here a continuous surface distribution, we need to take elementary strips over here. So, through the elementary strip on the surface we have to consider, as I discussed already, electric flux through the surface. We have to segregate the surface into a number of elements. So, over that element the electric field passes over here, E is equal 1 by 4 pi epsilon naught, point charge is Q and the distance of course R square. Let us suppose if there is a point charge is present over here, over this point charge there is a sphere is present, the sphere is covered over here. Then at any position if I consider on the surface, the distance remains same. So, the electric field of course it is remains always 1 by 4 pi epsilon naught Q by R square, and its area vector will be dA, is perpendicularly outward direction. So, angle between those two is 0, EdA cos theta. So, the electric flux is equal, small elementary area I consider, so small elementary flux. So, small amount of flux d phi is equal EdA cos theta, where theta is 0. Since electric field and area vector both are same direction over here, in place of electric field 1 by 4 pi epsilon naught Q by R square, and then dA and cos 0 value is 1 of course. Then we have to integrate the total flux over here. When you integrate the total flux, of course you can write directly also the total surface area, it remains constant. So, the flux phi is equal 1 by 4 pi epsilon naught Q by R square integration of area. So, this total surface area if you observe over here, the total surface area is equal to 4 pi R square. So, when you integrate the total surface area, we will get over here that Q upon 4 pi epsilon naught R square into 4 pi R square. 4 pi R square gets cancelled, the flux through the surface or closed surface is equal to 1 by epsilon times charge present within the surface. So, here in the expression whatever we got a result, that is does not depends on the shape. Suppose if the shape is like this, if it is there and over here the charge is present over here, then the flux through the surface, through the irregular surface, if I ask you, will get the same result as that, electric flux is equal 1 by epsilon naught times charge present over here. We are going to discuss coming section the Gauss law, the statement of Gauss law represent in this format only. Total flux is equal 1 by epsilon times charge present within the surface. So, we got over here that flux through the spherical distribution I consider over here surface Q by epsilon naught. If I consider any kind of shape, any kind of regular shape, the charge present over here is Q, then the electric flux through the surface always equal to Q upon epsilon naught we can say. So, flux produced due to a point charge is Q by epsilon naught we can say. Suppose flux calculation by a region of varying electric field will calculate. Flux produced by varying electric field. Up to now we have discussed that electric field intensity as a constant. We are assuming that particular point and then we are finding. Suppose flux calculation in the region of varying electric field. Flux calculation in the region of varying electric field. Let us suppose the electric field I am considering as present over here is a function of distance, that is E is equal to E naught x square if I say. The surface as given that the object or surface is given that in this type, let us suppose the surface is given like a cubical shape like this. Let us suppose the surface is given like this as a cuboid. The first end of this cube touches at a distance of 2a from the origin, if I say, and the side of the cube is, let us suppose, a. The side of the cube is a, if I say. Then electric field intensity with respect to distance, if I consider. So the electric field lines are entering over here and then exiting, of course. So the electric field lines are entering over here, if I say that E naught into distance, flux entering, phi 1, I am indicating that E naught into x square. Here x value is nothing but 2a whole square, and then area. What is the area present over here? We can say that surface area is, the area of this side is that a square, we can say. The flux entering is equal 4 E naught into a power 4, we can say, flux entering over here. Then the flux exiting, that is phi 2, I am indicating over here that E naught into, this is flux entering to the cube, flux entering into the cube, and here flux exiting over here through the cube. It is outside, if you consider over here that. Then of course the distance over here, side is a over here, then this end it is touched with obviously 2a, of course. This end is 2a, and then this is length is 2a from this distance, and 2a plus a will be, obviously this position will be 3a. So E naught into 3a whole square into, and then side over here that a square. So phi 2 is equal 9 E naught a power 4, we can say. Then the net flux, if we consider over here that phi 2 minus phi 1, 9 E naught a power 4 minus 4 E naught a power 4, will get as over here that 5 E naught a power 4. See, as we already know that yesterday, flux entering is negative and flux exiting is positive, and the total flux is equal to 5 E naught a power 4. If I use as a area vector over here, that area vector is opposite side over here 180 degrees, cos 180 is minus 1, that the total flux is equal to 9 minus 4, 5 E naught a power 4 also we can say, of course. So this is about your electric flux calculation. Now I will discuss the concept of solid angle as a continuation. Here concept of solid angle is very, very important role to solve many numerical sums for advanced level problems. Here the electric flux calculation or electric field intensity calculation also we can say. So what is the concept of solid angle? Solid angle is a three-dimensional angle. Solid angle is a three-dimensional angle subtended at a given point in the form of a conical shape. Let us suppose this is a surface, if I say. This is surface, solid angle we will discuss. For the solid angle, if I consider, so these are the surface over here. The periphery points are A, B, C, D I am giving. So the periphery points are like this, A, B, C, D if I say. Then all the periphery points joined at a point for a given radius R, if I say over here that all the periphery points are joined to a particular point, then it looks like a conical shape over here. So the conical shape, if we consider, for example, if you see that the paper, if I fold in the form of a conical shape, that the laminar or the surface is over here, this is a surface, and over this surface all the points from the surface joined at a point. So this point, over this point, whatever the angle subtended from inside it looks, so that will be the solid angle. So solid angle is a three-dimensional angle, I can say, three-dimensional measurement angle, or it is analogy for a plane angle. Already you know that what is plane angle. See here, plane angle, if you consider here that whenever two lines are intersect, the angle subtended represents a plane angle theta. Same thing over here also, all the periphery points, if we join over here, that the vertex looks like a, over this vertex all the points will be joined over this vertex, and then it looks like a conical shape. and whatever the angle subtended over this shape, conical shape, so this angle is called solid angle, represented as omega, you can say. The symbol of omega is like this in this case. So here plane angle over here, that when two lines are intersect over here, whatever the angle subtended over here, this angle represent theta. So theta is a measurement for two dimensional, and the solid angle over here, if you assume over here that solid angle, it's a measurement for 3D point of view, we can say. So a solid angle, if you observe over here, once again the definition, that solid angle is a three-dimensional angle by a conical surface about a vertex, Or also in another way definition, a solid angle is a three-dimensional subtended by a surface at a point by joining all the periphery points at a particular point. Joining its periphery points over this gives the solid angle. So here theta, if you consider, let us suppose there is an arc, if I consider, this will be the arc over here, arc length as L, and the distance from here to here is small r, is the radius, if I say. Then the arc length is equal to radius into angle, then in place of theta, L by r I can say. So theta is equal to L by r, arc length by radius. So theta represents as L upon r in case of two-dimensional angle, plane angle, we can say. Now, whereas in this case, if you observe over here, that the surface over here is S, if I say, the surface and the joining all the points having a distance is r, then the surface upon r square, the surface area upon r square gives the solid angle. Our surface area is equal omega into r square, also we can say. Here arc length is equal to radius into angle, same thing over here also, r square into omega gives the surface area. Now, suppose if it is not a regular shape, here exactly I consider as a circular shape I consider. If I consider as a regular shape, let us suppose like this, if I consider. For the surface also, the joining all the points from the periphery of this surface gives the solid angle. The angle subtended over here gives the solid angle, we can say. Now, here solid angle represents as S by r square. Let us suppose that if the length is like this, arc length is looks like this, and then this is theta, and then arc length is equal radius into angle, that is L is equal to r theta. Suppose if it is not a perfectly makes over here, then perpendicular drawn will not be like this. Suppose it looks like this, if I say. The perpendicular drawn looks like this. Then we can extend over here. Whenever we are joining over here, at any points if you observe, the solid angle represents as a constant, of course. The periphery points anywhere, if I consider the joining all the points over here, the solid angle remains constant. Same thing over here also, if you extend over here, then its perpendicular will be like this. Then angle made over here is alpha, if I say that, then here we can say over here that theta is equal to L cos alpha. Over here its perpendicular drawn we can say that L cos alpha upon r, we can say. The radius is or distance is r, if I say. Then we will analyze the solid angle over here. How to analyze a solid angle? Suppose that a complete ring, if I consider. When I consider a complete ring over here, that as we know that arc length is equal to radius into angle. So theta is equal to L by r, we can say. So in this case over here, the total length will be equal to a circumference of the circle, that is 2 pi r. The radius over here is r, if I say, then the theta present over here, plane angle has maximum 360 degrees, we can say. So theta is equal to pi. The same thing over here also, the surface area, suppose a complete spherical surface, if I consider, it's a three-dimensional. For a complete sphere, if I consider, for example, for this sphere over here, then all the points are joined at this point. The angle subtended at the point O gives the solid angle. So if it is like a complete sphere, if I consider over here, that sigma is equal, as I told you, S by r square. So here completely the total solid angle if you want to measure for a sphere, the sphere is looks like this, and over the point if you consider, the surface area of the sphere will be 4 pi, the radius is r if I say at this point, of course 4 pi r square upon r square, the solid angle must be equal to 4 pi we can say. Over here, if the solid angle over the center, if you assume for the sphere, over the center over here, if you see, just now I took as a some part over here, then completely sphere if we consider over this point, the angle subtended for a solid angle will be 4 pi. Now we will analyze the relation between half angle and we will analyze the relation between half angle of a cone and solid angle vertex. So how to analyze over here? That let us suppose consider a conical shape looks like this at this point O, if we say over here, and then the half angle represents over here that this will be phi if I say, this will be the phi, and the radius of this conical shape is r, and then radius of this conical shape is r. I will consider to analyze the solid angle for a half angle with solid angle, I am taking one small elementary strip over here at an angle theta vertically. At an angle theta vertically, the angle present over here is the d theta. So this should be r d theta, and the angle present over here is theta, r d theta we can say. Since over here theta over here, the radius of this strip must be equal to r sin theta we can say. So we can take these elements over here, that completely over here as radius as r we can say that 2 pi, the area of this element is equal 2 pi into radius over here that r sin theta into r d theta. So dA is equal 2 pi r square sin theta and then d theta. This will be the elementary strip area we can say. So we can consider here up to this extent, if I say the vertically it makes an angle phi. So we have to integrate from 0 angle to up to this phi angle over this completely radius r, if we want to touch this point, then 0 to phi. So we have to integrate over here from 0 to phi. When integrate from 0 to phi, integration of dA is a and 2 pi r square into 0 to phi sin theta d theta we can say. We are finding over here relation in half angle of a cone and solid angle vertex. Relation between half angle of cone. Half angle of cone represents like plane angle, that is phi. Half angle of a cone and solid angle with vertex. Solid angle at vertex. This is the relation we are finding. So the relation between half angle and then solid angle, if you observe that at this point the angle measurement will be like a solid angle we can say. As I told you that the basic analysis over here, that plane angle if you say L by R and solid angle if you say omega is equal S by R square. These are the 2 points we have to remember. Then here A is equal to 2 pi R square into integration of sin theta will be minus cos theta. Minus cos theta from 0 to phi. Here minus you can bring out over here minus 2 pi r square into cos phi minus cos 0. Here phi is a half angle of a cone. It is like a plane angle as I told you. Then the area is equal to 2 pi r square into minus, if I multiply over here, minus cos phi plus cos 0. So that is I can write over here that 1 minus cos phi. So here area is equal to 2 pi r square into 1 minus cos phi. Since as I told you over here that the area is equal to sigma times, here radius is r we assumed over here with respect to the vertex O, the distance is O, or area is equal to sigma into r square if I substitute 2 pi r square into 1 minus cos phi. Here r square gets cancelled, then omega is equal to 2 pi into 1 minus cos phi. This will be the very important relation for a solid angle with half angle of a cone. Over here, solid angle and half angle of a cone, if you observe over here, that let us suppose a semicircular ring if I consider. For a semicircular ring, the half angle will be theta is equal to, we can say over here that 90 pi by 2. So, theta is equal to 90 if I say that, or the half angle if you say over here that cos 90 is 0. So, omega is equal to 2 pi into 1 minus, the total angle is of course 2 pi, the plane angle total angle is 2 pi, but the half angle when I say over here that 90 cos 90 over here 0, then omega subtended over here. For the semicircular sphere, whenever I consider over here for a semicircular sphere, the omega is equal to 2 pi we can say. Suppose the sphere, if I assume like a spherical, it is like a complete sphere, it is not a part over here. For a complete sphere over here, the half angle we can say over here that 180 degrees. Then the sigma or omega is equal to 2 pi into 1 minus cos, here half angle is 2 pi, half angle is pi, because a complete angle for a semicircular angle is 180 but half is 90. In this case over here complete angle will be 2 pi, half angle will be 180. So, cos pi is minus 1, then omega is equal to 4 pi we can say. So, in this case omega is 4 pi. As I discussed just now, for a complete sphere, the angle subtended at the point over here, if you observe, in place of the total surface over here that 4 pi r square, then omega is equal to 4 pi r square upon r square, it should be 4 pi. And the unit of solid angle is that steradian, and unit of plane angle is radian. So, radian measurement is like a 2-dimensional and steradian measurement is for a 3D angular measurement. So, here omega present over here for a complete angle as 4 pi steradian SR. Here also by using this formula also we can say straight away that relation between half angle of a cone and then solid angle over here, omega is equal to 2 pi into 1 minus cos phi. This is the concept of solid angle, and then I am going to continue the next concept as by using a solid angle how to measure